my project is on the conservation of momentum by Aubrey Greenwood. So this is the picture for our problem, and it is when block A slides down and collides with block B, and then they slide together. Block A has a mass of m, and block B, which is identical to block A, also has a mass of m. And r is the radius of the quarter circle that they're in. And you can see as block A slides to block B, there is no friction. But as they slide together from Y to P, the distance L, we see we have friction. Now, if we go by our picture here, we can find, so that to use later on, that the friction equals mu, and mu will equal mu Fn. And then we see that the height, right here, this height, is going to be equal to r. And that the distance for Y and P here, for D, will be equal to L. So, first thing, we're going to draw the little pictures or whatever, and you see that this is block A, this is block B, and as block A, whenever it slides into block B before they actually collide, that is energy because it is moving. But after they have collided, right around here, after they've collided, it becomes momentum because they are now sticking together. So our first question is, determine the speed of block A just before it hits block B. So in order to do this, we'll look back here and we'll see that it is energy. And when it comes to energy, you know we have EO equals EF. Initial energy equals final energy. So the initial energy, we can see that it has a height for initial, so but it's not moving. So we know that it will be mgho equals, and for final, we see that it's moving as it's sliding down, but it has no height. So we get mgh equals 1/2 mv squared. And then our m's cross out, and if we look back, we see that, hey, height is equal to the radius. So it becomes gr equals 1/2 v squared, which becomes 2g times r equals v squared. We find the square root of both sides, so 2gr is equal to the velocity. So that square root of 2gr is the speed of block A before it hits block B. So right here, that its speed is square root of 2gr. Our next question is, determine the speed of the combined blocks immediately after their collision. So now, let's look at our picture here. We see it says, determine the speed of the combined blocks immediately after the collision. So after the collision, we see we've got momentum here. And what exactly is momentum, or the conservation of momentum? It is when two objects collide in an isolated system, the total momentum of the two objects before the collision is equal to the momentum of the two objects afterwards. Or, basically, initial momentum is equal to final momentum. PO equals PF. And with that, we see that if we just set it equal, PO equals PF. So we'll look at our picture here, and we all know that M, so it'd be MV U1, and then for right here, we have M1 equals V1. Now, for the final momentum, we see it gets a little tricky because we have two masses here, not just one, because they decided to stick together and keep sliding. So, we see that we'll have to add the masses together, m1 plus m2 times the final velocity. Now, the final velocity is what we're trying to find. We're trying to find this. So, let's plug in what we have already. And we know from the first equation that v is in fact equal to the square root of 2gr. That is equal to m1. And with these, since block A and block B are identical, when we do m1 plus m2, we can actually say 2m because they are identical. And it's just like adding the same masses together. So with that, now we can divide both sides by 2m. So we get m1 times square root of 2gr over 2m equals vf. But we're not quite done yet, because since these two masses are equal, that means they go away. And we're left with vf equals square root of 2gr over 2. Now, C says, assuming no energy is transferred to the track or to the air surrounding the blocks, determine the amount of internal energy transferred in the collision. Okay, now probably wondering exactly what internal energy is. So, what is internal energy? It is the total energy contained by a thermodynamic system. And it's the energy needed to create the system. And it has two main parts. We have the kinetic energy, which is due to the motion of the system's particles, or the potential energy associated with the static rest mass energy. Now we see the kinetic, motion, the motion of the energy, or when it's at rest. So if we look back at our picture, we see that the internal energy does not involve potential, because it's going to be moving. It's a moving potential, moving kinetic energy. And so we want to find the transfer of the kinetic energy, because as block A is coming down, it's colliding with block B. And so we want to find how much energy block A is transferring to block B. So in order to do that, we have to find the kinetic energy that is lost. So we have final kinetic minus initial kinetic. And that is equal to 1/2 mvf squared minus 1/2 mvo squared, which in turn will give you 1/2 2m, because we have our two masses, times 2 square root of 2gr times square root of 2gr over 2 minus 1/2 m times square root of 2gh squared. Well, r squared. Now, and then we got these two will cancel each other out. So we're left with m times the square root of 2. Well, not even, because we had to square that. So it is 2, that's 2gr over 4 times m minus 1/2 m times 2gr and this will equal 2 mgr over 4, which can be simplified to 1/2 minus it's 1/2 m times 2gr. These will cancel out, and we're left with mgr. So 1/2 mgr minus mgr will give us negative mgr over 2. And our final question says, determine the additional thermal energy that is generated as the block moves from Y to P. Now, if we look at our picture, well, in the picture we know that whenever it is